Okay, thank you very much. So let's thank Germán again. The following talk is given by Robert Weih, the head of the Department Chief Development at nanoPlus Nanosystem and Technologies, and he will talk about the laser technology for the mid-infrared and applications.
Okay, thank you for the kind introduction. My name is Robert Weih. I did my PhD at the University of Würzburg in Germany, and now I'm working for the company of nanoPlus in the chip development department and epitaxy. And I will combine some topics of the last two talks. The first talk, I want to take the sensing part, and from the last talk, the wavelength area, the mid-infrared, and I want to talk about laser technology for the mid-infrared and their applications, and I want to focus on some rather new kind of laser source, interband cascade lasers. So I want to introduce this kind of laser and give you some idea what is interesting about them and what they can be used for. So I want to motivate the topic, introduce you to the ICL material and the latest improvements that we had in our company, talk about single mode ICL DFBs, whereas the ICL chips can be used as gain chips as well. Want to talk about multi-emitter ICL DFB arrays, and last but not least summarize the topic and give you some future prospects. So to motivate the mid-infrared, why is it interesting to go from the near-infrared or the visible light sources to the mid-infrared, especially in tunable laser absorption spectroscopy? It is shown here quite impressively. There are absorption spectra of 3 different gases, methane, formaldehyde, and CO2, just as an example. And I divided the spectrum here in the near-infrared region up to 3 micron wavelength, and the mid-infrared starting from 3 micron. And as you can see, the normalized absorption, the absorption strength in the mid-infrared region is at least 1 order of magnitude stronger. So this, if you use it for absorption spectroscopy, gives you an increased sensitivity in systems, increased speed, and you can miniaturize your sensors. And as you can see here, you have a whole slew of gases in the mid-infrared section, especially if you look at the gases like CO, CO2, N2O, and NO, which have really strong absorption lines in the wavelength range between 4.2 and 5.6 microns. And they have been getting much attention within the last years, obviously due to environmental topics. So just to give you 2 applications what tunable laser absorption spectroscopy is used for. The first one is MAP. It's modified atmosphere packaging, and if you package food, you want to have it in a certain atmosphere. For example, if you have meat, there's a protein called myoglobin, and it's changing its color depending on the content of oxygen that you put in there. So this is rather a cosmetical issue because depending on the amount of oxygen you put in there, your meat stays red and looks kind of fresh, or it turns brownish, which gives you like an impression of old meat. But in other things, for example, fruit and vegetables, if you have a reduced oxygen content, it stays fresh longer because you decrease the oxidation process. And this is rather in a wavelength region in the visible or near infrared, because oxygen is typically detected at a wavelength of 763 nanometers. So this can be done with a conventional DFB diode lasers or even VCSELs. The advantage of this method compared to older methods, like taking a sample with a needle, is that you have less waste and you can automatically inline detect all the samples rather than taking a sample every couple of minutes and you have to destroy them, you have more waste. So this dispersive measurement of the gas concentration inside the package has some really nice advantages. Second application where we move into the mid-infrared is an automotive application where you want to measure exhaust gases like N2O, CO, CO2 or NO. And in a project together with the company Knestel, we developed a sensor which should be usable in ppm detection range and which should be quite fast. So it should have a rise time of 1.5 seconds. And another really important thing was that the system should be quite compact because you want to use it in a test stand for stationary use and you want to use it in a car or behind the car while it is driving, just in case this gives you some differences in the exhaust. Now to introduce why the mid-infrared or introduce the ICL concept where it fits into in the spectrum. I made a slide with the semiconductor laser concepts that exist in the near-infrared and in the mid-infrared region. So here, starting from the visible up to 3 microns, as we all know, there are 3 basic substrates existing where you can grow lasers on. This is the gallium arsenide for the short wavelength up to the lower telecom band, indium phosphide lasers in the typical telecom wavelength range, and gallium antimonide based lasers which have been demonstrated, I think, DFBs up to 3.4 microns. So they utilize type 1 transitions in a conventional geometry. From the longer wavelength section, the QCLs are emerging on indium phosphide substrates as well. They can cover a really wide range in the infrared region, and they have lots of output power. So you might be questioning yourself, why should you use another laser if you can cover all this? And the thing is that due to the intraband transition, which has some disadvantages, QCLs typically have a voltage that they have to be operated which is above 10 volts, which is specifically for like handheld devices. It's a lot of voltage and a lot of input power that you need. And this is where the ICL comes into the game. I want to focus on the ICLs based on the gallium antimonide substrate, which don't need to use such a lot of cascades and can be operated typically in a 3 to 4 or up to 5 volt range, and with currents that are rather in the range of typical diode lasers. So to go into the concept a bit deeper, the central element of the ICLs is this W-shaped quantum well. The transition energy can be tuned over a wide range with just changing a layer thickness, specifically this indium arsenide layers here that surround the ternary gallium indium antimonide layer here. So by changing those layers, you change the quantization energy of the upper level here. You can shift it upwards and downwards, and you're more or less independent of the band gap of the materials, which is like rather essential in typical diode lasers for the wavelength. And as you can see in this graph here, by changing the indium arsenide layer thickness, you can change the wavelength. Here in gray is marked the interesting market range for us between 3 and 6 microns, which has been realized. The drawback is that if you're moving this level down here, you see that the probability density shifts outwards and the spatial overlap of the quantized levels here decreases, which gives you some drawback if you go into longer wavelength ranges. This specifically, I want to talk about the region that I've talked about before, the 4 point something micron region. And what we realized when we were fabricating lasers from, let's say, 3 to 6 micron is that you have a drop in the characteristic temperature, which is the increase of the threshold current with temperature. And this is really essential for you want to have a high characteristic temperature to have a laser which operates in CW, or continuous wave operation, at room temperature and above. And here you have a drop in this T0 value, which we wanted to look into in more detail. And we found out that this is due to some resonances in the valence band. So let's say here at a shorter wavelength range, let's say 3.3 microns, you don't have a resonance. If you take the transition energy from the conduction band to the valence band and you transit it down here, there are no states where you have this. There are no states which can absorb. But if you go to this wavelength range here, you have like this resonance. The transition energy transfers right into this resonance, which gives you a high intervalence band absorption, high losses, and we call it final state optimization, what we did. So the quantum well, we changed it in thickness and the content, and we changed the indium level from 35 to 40% in this case, and changed the thickness of the ternary layer, which doesn't give you too much change regarding the wavelength or the spatial overlap, but the final state will optimize, and thus we could find, by changing here, as you can see, the content to 40% and the thickness, we could move up the T0 value, especially in the 4 to 5 micron range, from values around 40 here up to 60 around here for this specifically interesting wavelength range of the environmental important gases. So this will give us higher CW operation temperatures, and for the customers, they always want to operate, let's say, at least above room temperature without cooling. Showing you here some results of broad area lasers that we typically process to have feedback to our guys from epitaxy. So we have shallowly etched broad area devices, which are etched 1.5 microns into the upper cladding. They're operated under pulsed operation, and we were able to reduce the threshold current density from 600 amps per square centimeter down to 440, increase the characteristic temperature, what I've shown you, and increase the differential output power, so the slope of the IV curve, of the IP curve from 140 milliwatts per amp to 190 milliwatts per amp. So this, the reason for this must be a reduction of internal losses, so the intervalence band absorption could be reduced, which gives us higher performance, which I will come back to when I've introduced the DFB concept. So on ICL material, several DFB concepts have been demonstrated. All of them, like with all technology, have some advantages, some disadvantages. So buried gratings have already been realized. The disadvantage of this is that gallium antimonide technology, especially regrowth technology, is not that advanced, that it's really good and reproducible. You can use vertical sidewall gratings, or you can use germanium gratings on top to select your wavelength to have like one longitudinal mode. And the concept that nanoPlus is using is we're applying lateral metal gratings, which have the advantage that you have the DFB effect and that you have a wavelength dependent loss. So we give all the modes except the one that we want to have a higher loss. So we end up with only one mode and one wavelength that the laser emits. So here showing the technology in some more detail and some SEM pictures. So this is the ridge with the electroplated gold for heat removal. Up here, the ridge from the front. So here you have the passivation layer and the opening for the contact to introduce current. And here you can see the metal grating on the side of the ridge, which gives you feedback or introduces the periodic loss. And the technology is based on electron beam defined waveguides and gratings, then a dry etch step to define the ridge, silicon nitride, silicon dioxide passivation layers, and in the end contact metallization and electroplating gold on top. Here two examples of some DFB lasers. So this is the shortest or the ICL DFB with the shortest wavelength that has been demonstrated in the section between 2.7 and 2.9 microns. And as you can see on one epitaxy, the gain of these ICLs, it's quite wide. So even in this, I call it short wavelength range, we have with one epitaxy an accessible wavelength range of over 150 nanometers, and in longer wavelength ranges we have demonstrated more than 300 nanometers of accessible wavelength range with one epitaxial design. And here's an example of a rather long wavelength ICL DFB device beyond 5 microns. So the wavelength selection is governed by this formula, which is basically just a Bragg equation. So coming back to the optimization that I've introduced before with the 4.x micron ICLs. So this was based on the epitaxy that we've been using before making the lasers. So we were barely able to operate them in CW operation up to 10 degrees Celsius, which always needed cooling, especially in rough atmosphere at, let's say, power plants or something. So we introduced this new epitaxy, what I've shown you, and as you can see here, the lasers can be operated now in CW almost up to 40 degrees Celsius. We can reach a tuning range of more than 20 nanometers with current and with temperature with the ICL DFB devices. As you can see, operation voltage is around between, let's say, 3 and 5 volts, which is the most significant advantage over QCLs. And the tuning speed is roughly half a nanometer per Kelvin and 0.17 nanometers per milliamp, where the single mode here tunes in wavelength, and that you can scan an absorption line of a specific gas width and get your signal and your absorption strength. So coming to another application, because customers always want to have, let's say, modules or more functionality. So we had a question, can you detect two gases with one chip at the same time, which absorption lines are rather further apart than the typical tuning width. So this was the application, the cloud process, which is the most significant process for desulfurizing elemental sulfur from gaseous hydrogen sulfide. So the goal was to measure SO2 and H2S at the same time for a real-time control system. So what you want to do, you want to choose a wavelength region where you can detect both of them and you don't interfere with water absorption too much. So here around 2.6 and around 6 micron you have a lot of water absorption. So this gives you the feature, the two features here, the wavelength window, and that you want to operate around 4 microns. So we choose an epitaxy, an ICL epitaxy around 4 microns with a high characteristic temperature of 50 Kelvin and a low threshold current density. And we operated multi-emitter ICL DFBs. So we changed the design somewhat. So the electroplated gold goes into two directions, so we can bring the lasers closer together, which gives us some advantage when you want to come into fiber coupling, or if you want to go into focusing the lasers. So we have a pitch of 70 microns here, which can be reduced even further if you reduce the electroplated gold thickness here, or if you put other grooves in here, because of course if you bring the lasers too close together, your thermal crosstalk is too high, and if you operate one laser then you heat up the other laser, so this gives you some limitations regarding the pitch. So in the end we fabricated this multi-emitter structure and as I said, with a pitch of around 70 microns. Here are the LIV characteristics shown. Threshold currents around 20 milliamps, which is really low for mid-infrared devices, were reached. Here the lines represent the areas where the laser is operating in single mode, and the output power is sufficient for most absorption or for most TLAS applications. So we can reach output powers, let's say, between 5 and 10 milliwatts, as I said, which is sufficient for most of the applications. The two single mode channels are further apart, as I said, than the typical tuning width of 1 DFB. So here it's 90 nanometers. We can reach tuning ranges of 8 nanometer with current and around 20 nanometers, as said before, with the current and temperature. And the tuning speeds are 25 nanometers per watt or 0.14 nanometers per milliamp. And we measured thermal resistance of the chips of 64 Kelvin per watt. And as I said before, the thermal crosstalk is 11 Kelvin per watt. So this is 4 nanometers per watt, what the wavelength changes in the neighboring laser device. And in the end, you want to measure the gases. So here you have the absorption lines of the H2S. So you can choose one of them, scan over it, measure quantitatively the content of H2S. And then you choose an absorption line. I think this one was chosen because it has the lowest interference with the H2S absorption lines to measure the SO2. So you have both gases that you can measure and optimize the process of desulfurizing. We took it in another project, we took it even one step further because we had a question, how many lasers or can we even cover more channels? So we produced multi-wavelength arrays. We had an array with 9 emitters, and we had a system with covering 2 times 4 channels. So the advantage, as I said, of the ICL is that it covers a bright or a really broad wavelength range of up to 300 nanometers. And we know the material really good from a normal DFB process. So we can say, okay, each laser should have a certain wavelength or a certain wavelength window which it covers. As you can see here, several emitters on this array, and here in a normal microscope picture. So here in this case we put lasers or laser arrays with 4 channels into 2 TO66 housings, which are the standard housings that our ICLs are packaged in. And as you can see here, we're in the wavelength range between 3.3 and 3.5 microns, where lots of hydrocarbons have strong absorption lines. And with current and temperature, we were able to cover here with one housing. We have the lower wavelength section, and in the other housing 4 channels for the longer wavelength section. And we were able with the 2 packages to, let's say, address 8 wavelength channels, or with a multi-wavelength array that we fabricated on one chip. So we have 9 laser structures covering 9 channels with a wavelength range of more than 200 nanometers. So here you can see the shortest one lying just below 3.3 micron, and the longest one almost reaching 3.5 microns. And just to sum up, or just to show you what the application was, it was a target application at the Preem oil refinery. And the gases that had to be measured were methane, ethane, propane, butane, and pentane. And before this system was introduced, you had to extract the gases, which gives you 60 liters per hour of sample gas that has to be vented in order to do gas chromatography, which also took more time than a live measurement of all the 5 contents with one sensor. And as you can see here, the sensor that was developed by the Polish company Air Optics is quite compact and just fits into one 19-inch rack, just a couple centimeters high. So this is quite a compact system, which was developed in the IC spec project. So to sum up the ICL technology, we have developed DFB ICLs in the mid-infrared range between 2.8 and 5.7 microns, which have low threshold power of around 100 milliwatts, which show fast tuning, room temperature CW operation, and we have fabricated customer-specific multi-wavelength arrays. And in the future, the ongoing optimization will go into even longer wavelength. We want to reach up to 10 microns with the ICL, which in principle should be possible. we want to reach wider tunability and more flexible multi-wavelength devices. And of course, what most customers ask for is higher operation temperature and output power. So this is another fact that we're going to invest research in. So with this, thank you for your attention.
Thank you very much, Robert, for your nice presentation. Are there any questions? Okay, I have one by myself. You have some multiple of applications about mid-infrared. Have you seen or have you noticed an incremental demand on these kind of devices in the last years?
Yeah, within the last year with the environmental technology, especially because the devices are light, we have some applications that are measuring in different heights with drones, because in drones you want to have light systems. There we have lasers, then with the car industry, and also with the we have some projects regarding space applications, such as measuring different contents, and there you want to have a low input power, and if you want to have a mid-infrared laser, you rather go to ICLs than QCLs.
Thanks. Are there any other questions?
A very nice presentation. I was just curious why those chromium gratings? Why do you use those as opposed to normal gratings?
I think this is one. You mean why in general metal gratings, or just why chromium?
Why metal?
Okay. Metal is just because it introduces loss. You have the complex refractive index of the metal is quite high, so you introduce periodic loss. So if you see all the different longitudinal modes, you have this one mode which experiences the lowest loss, and this is a quite stable system. So all the other modes have a higher loss because they interfere with the metal grating more. So as I said, this is quite really a stable system, and you don't, for example, if you use this grating, we have worked with the sidewall gratings here as well, which are quite dependent on the edge quality, so you need like really steep sidewalls. So we had the way higher yield with this metal gratings.
One last question about that.
Yeah. Hi, Timo from VTT Finland. So questions, have you already integrated this with the passive waveguide circuits, doing some multiplexing and things like that? And do you think that could be done like a monolithically someday, or is this always going to be hybrid integration?
I hope so, that this will be able to integrate it. As I said, it's thinkable to have gain chips and wavelength selective elements like circled waveguides or something like that. And I think the highest or the most important thing is to have waveguides with low loss in the mid-infrared region. So this, I think, will be one of the most interesting tasks to realize. But I hope this will be able to integrate with a higher functionality into PICs.
Okay, thanks.
Okay, so let's thank Robert again